let's make it a little bit complicated, okay? But also simpler at the same time. In this slide here, we're trying to see the relationship between R naught and the average age at infection. So let's assume that the infection that we are dealing with here gives immunity after infection, like measles. When you're infected with measles and you develop immunity that protects you against further infections in the future. Let's also assume that we have a rectangular age distribution, meaning that life expectancy is very constant. Is a constant in a population. So we have these two assumptions here. So we can estimate the proportion of susceptible. So in a population of susceptible and where some people are susceptible and some are immune, the proportion of susceptible is given by this relationship 1/R naught. And we can also estimate in a very different way the proportion of susceptible looking at the age at infection. So this is the overall life expectancy, and people get infected at some point, and we have the average age at infection. This is represented by the capital A. Their proportion of susceptible is simply dedicated by doing A over life expectancy. There are some mathematical background below. On the background to arrive to this formula. But I think understanding this is enough for you to understand the relationship between R naught and the average age at infection. So because the susceptible can be estimated by 1 minus R naught, and it can also be estimated by the average age at infection over life expectancy, we can come to this relationship between R naught, average age at infection, and life expectancy. This showing us something very interesting. Remember, we say that life expectancy is a constant. So a constant doesn't change over time. It remains the same. So if R naught is small, if we want to keep this the same, the average age at infection should become large so that life expectancy is kept constant. If R naught is large, in order to keep life expectancy the same, the average age at infection will become low. So technically, this means that infection with very high reproductive number, people get infected at lower age. And if the infection has a very small reproductive number, people would get infected at much later age. We have I have a graph for you here showing 3 infectious diseases that can induce immunity. We have measles, varicella, and mumps. So what do you see here? You see that people with measles get infected much earlier, at when they are 5.6 years old. With varicella, it's 6.7. With mumps, they get infected when they are 11 or around 12. So why? Because measles has a much higher R naught compared to varicella, and varicella has a much higher R naught compared to mumps. So if R naught is very large, you get infected when you are very young. When R naught is very small, you get infected later in age. So this is the relationship between R nodes and the age at infection. Another important relationship to look at is the relationship between R nodes and the average age at infection, but based on the settings, urban and rural. For example, you see, even for the same disease, we have in green here, measles. Even for the same disease, the age at infection is different when we are in an urban area compared to when we are in rural area. Why? It's because we can come back to this formula here. Remember, we said that R naught is the rate at which people contact each other, the probability of transmission, the duration. So in urban area, we have high population density. This means that people have high contact rates. In rural area, we have low population density. People contact, and the contact rate is much lower. So in urban area, R naught is much higher than in rural area because of the difference in terms of the contact rates depending on urban and rural here. So for the same disease, the settings and other elements here can influence the average age at infection. So again, we are in this formula here. R naught, our effective reproduction number equals R naught multiplied by the proportion of susceptible. And this is a very important element to keep in mind, is that the proportion of susceptible and R naught influence the dynamic of an epidemic. If the proportion of susceptible equals 1 over R naught, if we put 1 over R naught here, reproductive number will equal 1. And when it's 1, we have an endemic stage. If the proportion of susceptible becomes more than R over R naught, we have an epidemic. If the proportion of susceptible is lower than 1 over R naught, the epidemic will die out. So how many people are susceptible in a population is a very key characteristic that will tell you if an infection or an infectious disease will take off or not. So if everybody here is susceptible, if someone with infectious disease like influenza come, we all have the risk to get the infection. But if many people are not susceptible, meaning that they are immune, the infection will not take off. So the proportion of susceptible and R naught are key parameters for any epidemic. Whenever you hear there is an epidemic, you should always think in terms of the proportion of susceptible and R naught to have an idea about what's going on. So this is here showing you just what's happened. As the epidemic goes on, the attack rate increases. The proportion of susceptible goes down because some people become immune. And R naught also is going down. And at some point, when R naught becomes 1 means that we have reached a plateau, a stable point. So it's the peak here. And we drop at less than 1. When we drop at less than 1, the infection starts going down because R naught is less than 1. And it's the number of susceptible also goes down, meaning that people are becoming immune here. So at less than 1, the infection stops, the epidemic stops. So you can see the relationship between the number of new infections, the attack rate, which keeps on increasing. Over time, the number of susceptible decrease because R naught also decreases here. And this is the reason why some epidemics, we have these peaks here. Whenever we have an epidemic, when you look at a graph, there is a climbing point where more and more people are getting infected. Here, the proportion of susceptible is more than 1 over R naught. That's why the number is increasing. And it reaches the point where the proportion of susceptible becomes equal to 1 over R naught. The infection cannot increase anymore here. And then when it becomes less than 1 over R naught, the infection goes down. We don't have many susceptible, and the infection drops. The next wave will come only when the proportion of susceptible becomes greater. So that's why we have this warning over time of epidemics. So the factors to consider here, it's susceptible, the number of susceptible or proportion, and the R naughts. It was a little bit complicated, but it's gonna get much complicated here. So we're going to see some consideration about mathematical modeling of infectious diseases.